Okay, chapter 10.4, putting it together, which method do I use? Okay, so for hypothesis testing, right? What parameter is addressed in the hypothesis, sorry, that's how you decide. Is it a proportion or a mean? If it's a proportion, make sure that your three requirements they only use the one, right? But make sure we can say it's approximately normal, which means n times p sub naught times 1 minus p sub naught has to be greater than or equal to 10. Also, your sample has to be less than 5% of the entire population, and it needs to be a random sample. Then you find your z value, right? If it's a mean, your sample size has to be greater than 30, right? Or we've got to know it's already normally distributed. Okay, so, and if it's not greater than 30, then you check to see if there's any outliers before you can use this method. Okay, and then if those conditions are met, we use the t distribution, and so we find our t value, and here's the formula for each of those. So let's just look at a couple of examples. All right, a simple random sample of size n equals 200 individuals with a valid driver's license is asked if they drive an American-made automobile. Of the 200 individuals surveyed, 115 responded that they drive an American-made automobile. Determine if a majority of those with a valid driver's license drive an American-made automobile at the 0.05 level of significance. Okay, so first of all, I have to decide this is a proportion. We've just got 115 out of 200. We don't have a mean or any talk of an average in there. So the first thing I've got to do is make sure that n times p sub naught, and what we're looking for here, the question is determine if a majority, right? So that means over half. So we're looking at, is it half or more? So 0.5 times 1 minus 0.5 is 0.5. I got to make sure that that's greater than 10. Well, I don't even need a calculator for that, right? Half of 200 is 100, half of 100 is 50. So that's greater than 0.10. Okay. Also, our sample is 200. That's way less than 5% of the Americans with a driver's license. And it's a random sample. So our three requirements are met. That means our null hypothesis is the proportion actually equal to half of the population or more than half, a majority, right? Or more than half. Okay, because it's a proportion, we need our p hat, which is 115 out of 200. Okay. Or 0.575. All right. Let's find our z value. All right. So 0.575 minus 0.5 divided by the square root of, remember we've got our formula, so p 1 minus p over n. Okay, let's see what that is. 2.12. Okay, and so my question is, if I'm just doing the classical approach, we say if it's over 2 standard deviations, then we're going to reject H sub naught. This is 2.12, so we're going to reject H sub naught. Okay, if I wanted to do the p-value approach, right, we're going to enter that in our calculator is the easiest thing to do for there. So let's hit stat, go over to tests, and then go down to number 5, right, the 1 for one variable. So all we have is one variable. Proportion z-test. Let's enter our information. P sub naught is 0.5, x 115, n 200. We're doing a greater than. So let's calculate. And we get that P is 0.016, or p-value 0.016. 0.016 is less than 0.05. So once again, we reject H sub naught, right? So there is sufficient evidence to conclude that a majority of people drive American-made automobiles. Let's look at another one. A psychologist obtains a random sample of 20 mothers in the first trimester of their pregnancy. The mothers are asked to play Mozart in the house at least 30 minutes each day until they give birth. After 5 years, the child is administered an IQ test. We know that IQs are normally distributed with a mean of 100. Okay, so this is normally distributed. I don't have to check any of my previous requirements, right? Because it's telling us it's normal. If the IQs of the 20 children in the study result in a sample mean of 104.2 and a sample standard deviation of 14.7, is there evidence that the children have higher IQs? Use the 5% level of significance. Okay, now, since this is only 20, and because we're doing this on a mean, right, on a mean, would need to be 30 or greater. If it did not tell me they were normally distributed, I have to create a box plot and see if there's outliers before I continue. Okay, if there's outliers, I could not continue. But because it tells us it's normally distributed, we're good to go. So our null hypothesis is that the mean, we know that IQs have a mean of 100. And our alternative hypothesis is that is there evidence that the children have higher IQs? Oh, that it's more than 100. So a one-tailed test, specifically a right-tailed test. Because it's on a mean, we need our t-value instead of our z-value. Okay, so the formula for that, okay, we've got our x bar minus the mean over standard deviation over the square root of n. All right, so let's plug that in. 1.278. Okay, so then I need to look on my chart, my t-value chart, And remember, it gives us the value for the right-hand side, and that's what we want. So perfect. So when I look on my t value at the 19 degrees of freedom, and I go over to the 0.05, right, 0.05, that intersection is at 1.729. So this is 1.729, right, our critical value. Okay, so this is 1.278. It's on this side of it. It is not in the critical region, so we do not reject the null hypothesis. Do not reject the null hypothesis. Don't accept it, just don't reject it. Okay, if I want to do the p-value, once again, that one we can do on our calculator. So I'm going to go into stat, over to tests, and choose that t-test, number 2. Okay, so we've got the stats as opposed to the data. So let's see. Mu sub naught is 100. X bar is 104.2. Standard deviation 14.7. N is 20. This is a right-tailed test. And it tells us that P is 0.1. P is 0.108. 0.108. So that is more than that. It's not unusual, right? So the probability of that happening is about 11 out of 100, not 5 or less. So that's not unusual. So once again, we fail to reject the hypotheses. You don't have to do both methods, right? You can pick either method, or depending on the problem, if it tells you which specific method. I'm just doing both methods as an example, right? It's also a nice double check for us. Say we're on a test, let's double check and make sure that we get that we're not going to reject the null hypothesis in both methods. Okay, one more. Suppose the mean wait time for a telephone reservation agent at a large airline is 43 seconds. A manager with the airline is concerned that business may be lost due to customers having to wait too long for an agent. Whoa, 43 seconds. Have you ever waited for anyone on the phone for 43 seconds or less? But it might be more like 43 minutes, right? Anyhow, sorry. Got distracted. To address this concern, the manager develops new airline reservation policies that are intended to reduce the amount of time an agent needs to spend with each customer. A random sample of 250 customers results in a sample mean, so it's a mean again, a sample mean wait time of 42.3 seconds with a standard deviation of 4.2 seconds. So use the 5% level of significance. Do you believe the new policies were effective? Okay, so we do our procedure. It's a 250 sample size, so I'm good there on the sample size. It was a random sample. 250 is less than 5% of the population. So, all right, let's see. I need a pen. H sub naught is, the mean was 43 seconds. And he's hoping that he lowered it. So we want to know if it's now actually less than 43 seconds. Because it's the mean. Okay, we're using the student's t again. So 42.3 minus 43 over 4.2 over square root of 250. Okay. And we get negative 2.635. Okay, so I'm going to look on my student's t distribution again at, let's see, 249. So I'm really going to look across the row of 100 because 249 is closer to 100 than 1,000. Going to go over again at 0.05, and I see that that intersection is at 1.66. Now remember, the student's t gives us this critical region, but we're at a less than, so what we're interested in is this. But because it's symmetric, I know this is negative 1.66, right, due to symmetry. So now I have to compare. Oh yeah, negative 2.63, that's way over here. That is indeed in my critical region, so I will reject that null hypothesis. There is sufficient evidence to conclude that the mean wait time is less than 43 seconds. Once again, just to check for our p-value, just to get extra practice at that, going to stat, over to test. Okay, t-test number 2, let's see, mu sum naught 43, x bar 42.3, standard deviation 4.2, 250 for n. Okay, this time we're doing a left-tailed test. So I get that p is 0.0045. Which again is considerably less than that. So it is very unusual, unlikely, right? Less than 1 time out of 100 this would happen. So there is sufficient evidence to suspect that the mean wait time is actually less than 43 seconds now. Okay, but this one has an extra question. Do you think the results have I don't know why it says a practical significance? Okay, well, if your wait time was 43 seconds and you changed it to 42.3 seconds, the wait time hasn't even gotten smaller by a whole second. Okay, does that practically matter if you're waiting on the phone for 42.3 seconds or 43 seconds? You're not even going to notice the difference. So no, it doesn't have practical significance, even though it's statistically significant, but practically it doesn't matter. Okay, that finishes up chapter 10. Yeah, let me know if you have any questions.